Hey there, I'm Prince. So I think you have already gone through the architecture diagram of Vault, and if you have not, then I'll link the video in the description. Feel free to go through. And now we can move on to the coding and testing part. So if you remember from our PDAs, uh, we needed two different kinds of PDAs. One of them was to store the data, and another one was to store the actual funds. So first thing while writing the contract that we need are to define what are the accounts or what are our PDAs gonna look like, right? So we have our first PDA, that was Vault State PDA, in which we were going to store the bumps of two different PDAs that we are going to create. One of them was Vault Bump and one of them was State Bump. So State Bump is basically the bump of this PDA itself, and Vault Bump is basically the PDA of is the bump of that PDA where we are going to store the actual lampports or actual Solana. And after that we have amounts, and another thing is that we need to actually calculate the space for this PDA and give it to the contract so that it can initialize on the chain. And as we know that in order to initialize an account on Solana chain, you have to uh, put some lampports in it so that it becomes rent exempted. So that rent exemption price depends on the uh, size of the accounts. So you can do it manually, as you know that Anchor uses by default 8 byte discriminator. So this 8 is for that, and 1 is for the U8 bump of the two PDs. And as you can see, our amount is U64, which makes up 8 byte. So this can be you can implement the space for Vault State, or you can do it automatically by using macro. So you can basically derive init space for it, so you don't have to do this, and it will automatically calculate and you can get it while writing contract. Since this is our first contract and we are gonna do everything manually, so I have committed this macro, and we are gonna use this implementation that we derived uh, our own. And as we know, after confirming the account structure for our PDA, the second steps that comes to writing while writing a contract is basically come to the instruction part. So as you know that our very first instruction is initialize instruction, and while writing an anchor contract, you have to basically focus upon two different things. One of them is for each instruction you have to define all the accounts that are gonna need it in this instruction and what is going to be the logic. So what exactly are we going to do in this instruction? So similarly, uh, as you can see, this is basically the accounts that we are going to need to initialize or call initialize instruction. First, as we discussed earlier, first is going to be the user who is going to be a signer. So this is the user who signs for the transaction and creates the vault. So as you can see, this account is mutable because he's gonna pay for this transaction, he's gonna pay for this vault state creation, he's gonna pay for the transaction. So it's mutable and he's the signer of this instruction for this instruction. After that we have our very first PDA, that is your vault state PDA. And since this is the first time we are initializing this, so this has init constraint. After that, for every init constraint, if you are initializing a PDA, you need to define who is going to pay for that initialization, who is going to pay for this vault state initialization. So as you can see, the user is the payer. After that you have to give the seed for this PDA so that it could be derived easily. So since this is our state, I have put a simple state as a seed, and uh, we want one user, we want the state to be specific to a particular user, so that we have used the user public key as another seed. So this PDA has basically two different kind of seed. One of them is simple state string, and another one is the user public key. After that, bump. And as you know, this is a PDA, so you have to put this space so that system program can initialize this account on chain and give the authority back to the user. So if you do vault state and if you call the init space function that we defined over here, that we defined over here. So this is gonna calculate the space. So there is one catch in this. If we use this one, so instead of using this one, if we use the derive macro, you'll have to put 8 over here, because by default this macro does not include the 8-byte discriminator. You have to manually provide it, but since we are using our manual implementation, and we have already included 8 over here, so you don't have to 8-byte discriminator over here, so you don't have to do it manually over here. After that, our third PDA, second PDA was a vault, where we are gonna actually store the amount, and the seed for the vault is a vault string, and we are using the counter public key of this first PDA as a seed for the second PDA, so that both of them becomes connected somehow, and we have our bump. After that, we need system program, since we are initializing 2 PDAs in our contract in this instruction, so we do need a system program. Mostly you're gonna use system program for every instructions. And after that, in implementation part, we are gonna write the logic. So if you remember, in our logic part, we are doing simple stuff, like we were creating the vault PDAs, updating the details, and we are creating the vault, right? So this init basically create the PDA. You don't have to do anything. And in the logic part, you just have to populate the data in it. So as you know, this part, if you do bump and you just give initialize bump constraint, it will automatically, Anchor will automatically derive the bumps for you, and you can basically get those bumps in bumps dot vault for vault bump, and bumps dot vault state for vault state bump. So there, here also we have as you can see, I'm doing two different thing, but these two basically do the same stuff. Either you can either you can populate the field one by one, or if you are about to populate the entire struct, you don't have to do it one by one. You might forget a particular field, so you can use this syntax, or if you're going to do it one by one, you can use this syntax. So basically I prefer this one, because since we are populating the entire field, you can use this one. After that, yeah, before moving on to the second instruction, that is deposit, let's discuss a simple stuff that we have already discussed. If you notice, you don't have any init constraint or pair constraint in the second PDA, because we have already discussed that the vault is simply a system account where we are going to store funds. So if you just transfer funds to a system account, it get auto initialized, and if you remove funds from it, it gets closed. You don't have to do anything. You don't have to initialize it manually like other PDAs. And yeah, after that we can move on to our second instruction, that was our deposit instruction. And if you remember, for deposit instruction we needed 4 accounts. First one was the pair, second one was our second and third were our 2 PDs, and the last one was our system program. And it's simple, same stuff. Here we have our user who is going to transfer funds from his account to the vault account. So you will notice both of these accounts are mutable, so that lamports in this account and this accounts are going to change. And after that, in our very first PDA, we have put this mutable, because if you notice, in our previous instruction we just put amount as 0, which we need to increment to the amount that user is going to put in our vault. After that, after that we have provided the same seed that we gave in the first instruction. And as you will notice, you don't have to calculate bumps over here, because we in the first instruction we calculated the bump and we stored in our vault state PDA, so you can directly use. So it is a good practice that you don't calculate bump every time. It's a compute unit expensive task, so it will eat away. This is going to make our transaction a little bit expensive, because it takes a lot of compute unit to calculate bumps. If you read about the PDA, the concept is very interesting, and you will find out why I'm talking to store the bump instead of deriving it every time. Similarly, we have our third PDA. This is also mutable because the user is going to transfer funds from his accounts to this vault. You will notice the seeds are same. And we need system program because we are going to use system program. So basically, when you transfer funds from user account to vault, so we basically CPI into system program, and we use transfer functions from system program. So even in a simple transfer, we are basically using CPI. So this is Solana, and yeah, this make things a little bit tough for developers to write the contract, but it makes the transactions very fast and all. And coming to the logic part, if you remember, our logic part was to transfer users funds from user to vault, and we just have to update the vault state PD, right? So if you'll notice, uh, in order to create any CPI, you have to basically provide what is the program that you are going to use. So in CPI program, you can notice we are using simple system program itself, and you have to provide all those accounts that you need. And since we have to provide basically for transfer, just need two accounts, from and to. So in our scenario, user is a user account is the from account, so we are going to transfer lamp ports from user account to the vault account. So it's like, it's understandable, right? I don't have to explain it too much. After that, the context is, so you will notice we have two different kind of context. One of them is CPI context dot new, and another one is CPI context new with signer. Since we are transferring funds from user to the vault, so user is going to be signer, right? So this transaction or this instruction is going to be signed manually by user, not by any PDA. So we are using simple new. But if this instruction would have been like opposite, if we were transferring funds from vault to the user, we'll have to do new with signer, and you have to provide signer seeds. This is also an interesting concept that we are going to discuss in the withdraw instruction. Yeah, and we provide our CPI program and all the accounts. After that, you just call the function with context and amount. And if you noticed, we are forgetting something. We have to basically we have to update the vault state with the amount, right? So you can do self dot uh, vault state dot amounts equals to amount, and this will basically update the amount, right? And yeah, coming to our third instruction, that was basically withdraw. And in withdraw instruction, we have similar accounts, the pair, the vault PDA, the vault, and the system program. And in this, the logic was to transfer funds from vault back to the user, and we have to update the vault state PDA. So we are gonna do same stuff over here. If you notice, uh, we have our user as a signer, and it's mutable because the lamp ports is going to change in this account. After that, we have our vault state. This is also mutable because we are going to update the state. After that, the vault, this is also mutable because we are going to change the lamp ports. We're basically going to transfer lamp ports from vaults to back to the user. After that, we have our system program. We are going to do simple same stuff that we did in our previous instruction of deposit, but there is going to be simple changes that if you remember, CPI program is same, system program, CPI accounts. This time we are transferring funds from vault back to the user. So from is vault and to is user. And there comes the interesting part, right? We already talk about new with signer concept, right? And since our previous instruction was getting manually signed by user on the client side, and this time we are gonna since we are gonna sign this using our PDA. So I'll tell you. Let's discuss about that. What is basically meaning of the signer, right? So when a lamport from any accounts is about to get decremented, right? This account has to be a signer. If we are decrementing amount of lamports from user was supposed to be a signer in this context. And since we are decrementing the lamports from vault, so we need vault as a signer. But vault is a PDA, right? And how can a PDA sign? And there's a very interesting concept in Solana that you can basically create signer seeds. You can derive signers from the seeds that we provided while initializing this PDA, and you can use that as a signer. And our contract our contract is gonna take all those seeds. This is gonna derive a signer seed, and this is gonna sign on the behalf of that PDA. So Solana is like quite interesting stuff happening over there. Just read about PDA and you will know. So if you notice in the seed part, you have to memorize this. Basically, we provide the same seed that we provided while initialization. That was the vault string. After that, vault state key. We have vault state key and bump. After that, you have to make it a particular signer seed, and instead of doing just cpa context dot new, we do cpa context new with signer, because this time signer is our PDA. We provide same cpa program cpa account, and there is going to be a additional field that is signer seeds. And yeah, after that we do same transfer, that with cpa context and amount. And yeah, if you remember, we have to update the field over here too, and I'll just go ahead and update it. That was to self dot vault state dot amount, and that is equals to, since we are transferring the entire fund, right? Since we are we can do minus equal to amounts, and we are not transferring entire fund. Basically, we'll have user uh, input how much amount he wants to withdraw from the vault. So we are going to just decrement it from the state PDA, and we can proceed to the third instruction, that is close. But before we do that, we have one thing, right? If you notice, in our withdraw account and in our deposit account, we are basically using same accounts, right? All of accounts are same. There is nothing difference. So this violates the dry principle of coding, which means to not repeat yourself. So what you can do basically is we'll comment this out, and let's make it something more generic. Let's make it payment. And yeah, we are gonna implement payment, and we can basically get this part from here, and we can do this, right? And yeah, this part can be commented. So yeah, you will notice we have since we are using same account in both of these two different instruction, you don't have to write it similar. You don't have to write it uh, on different principle on different places. You can just basically write it in a single struct, and you can implement two different instructions for the same struct. In our last instruction, this is basically close. What we are gonna do is we are gonna transfer the remaining funds back to the user, and we are gonna close both of our PDA, and uh, and then we are done, right? So since we are going to transfer the remaining funds from vault back to the user is going to be mutable, and he's the signer for this instruction too. After that, you will notice everything is similar, right? We have mutable, you have seed, same seeds, you have same vault, and there is a unique constraint over here, which is basically close, right? So just anchor makes your life easy to write smart contract, right? If you do just close equals to user, this will basically close this PDA after the end of this instruction, and this will transfer the rent back to the user. If you remember, while we were initializing our vault state PDF for the very first time, we discussed that it needs some kind of rent for rent exemption, right? It needs some lamports for rent exemption. And so since we are closing this PDA, so we are gonna take that rent and give it back to the user, because since he was the creator. After that, we have our vault PDA. You will notice it's just mutable because we are gonna transfer funds from vault, the remaining funds from vault back to the user. There is nothing nothing constraint used over here like close, right? So as you already know, this is a simple system account. You don't have to initialize it, you don't have to close it. If you put funds into it, it will get auto initialized. If you remove funds from it, it gets closed. Very simple. After that, we need system program. We are going to do same stuff in the close part, that we are going to use CPI program. We are going to transfer uh, funds from vault back to the user. And since this is uh, a PDA transfer, we are transferring funds from PDA to the user. So you have to do the same stuff that was new with signer, and you have to provide signer seats along with these two defaults like program accounts and signer seats. And we're going to transfer funds from the PDA to the user. And in this instruction, you will notice we are not taking any input from user, that how much amount he wants. Since he calls the close instruction, it becomes logically inevitable that we're going to transfer the entire funds from vault back to the user. So if you do self.vault.lampports, this will basically do what it will. This returns back the entire lampports in this field, and you don't have to manually close the first PDA. This is more than enough to close this PDA at the end of this instruction. And yeah, we are done with our all the instruction. And after that, we can populate those instruction in our so this is the last part where we take all the instruction and put it in our main function. So we have 4 instruction, right? Initialize, deposit, withdraw, and close. And initializing, we just basically call this initialize instruction. We provide the context, that was our the initialize struct. After that, if you remember, we combined the deposit and withdraw to use same payment struct, because they were using same account. And after that, this we call deposit function with the amount that we take from user as an input. And similarly, within withdraw, we take amount from user and we provide in the withdraw function. And the last one is close function. You don't have to take any amount as an input from user, because we're going to transfer the entire funds from user back to the we're going to transfer the entire funds from vault back to the user. After that, if you remember, we have something interesting over here. So this is what basically derives the bump and provides it to the uh, to our initialize function, and we can use bump over here, right? The code is ready, but how do we know it actually works or not? So in the next video, we are going to use Surfpool to test these instructions against a local validator.